Go, go ahead.
Well, a computing language is considered Turing complete when it can emulate a Turing machine
Okay.
and also run any Turing compatible program.
Okay, and what's a Turing machine?
Turing machine is a machine that has a specific set of rules, and you put input into it, and based off of the rules, the input makes a stream of data that tries to solve the problem.
Okay.
But it's not based off of memory or time consumed by solving that problem.
Are Turing machines real?
No, they're theoretical.
Okay, so the Turing machine is a theoretical machine based on an infinite length tape, right? That goes back and forth, and we can, every single time we're on one of the buckets, one of so think of the Turing machine like a big array. Every single time we're on one of the buckets, we're looking at a value. And we can overwrite that value just like a variable, stuff like that, and move back and forth, so we continually change states, potentially an infinite number of times. So a language or a problem is said to be Turing complete if it can be used, or language or a tool is said to be Turing complete if it can be used to emulate a Turing machine. Okay, number 2, what's a blockchain? What is the blockchain?
Well, all the transactions of a coin reside.
Okay, so it's the one place where all the transactions that have ever occurred related to a particular coin resides. Okay, fair enough. All right, questions about either of those? All right, so let's keep talking. So we're going to start talking about how mining works more specifically. We're going to get more into the details of the algorithm. At this point, we're at the 2,000-foot view. We're going to dive down to about the 200-foot view. And then after that, we're going to get down to the 2-inch view. And actually talk about the specific algorithms, how SHA-256 works, as well as the alternate algorithms like script. But generally speaking, we have these things called mining pools. And we talked a little bit about mining up until this point, where it becomes this giant guessing game, like it's a lottery. Okay, so if all of us in here, we're all mining Bitcoins, let's say, we're just making guess after guess after guess, seeing if our key unlocks the puzzle, whatever that puzzle is, and we'll talk about that today. Okay, so it's possible for any one of us to guess right first. Make sense? So if we all assume that we're the same speed, we can all guess at the same speed, none of us has an advantage over the other person, anybody else, correct? It's all random. Now, what if I could guess 10 times faster than any individual one of you? Do I have an advantage? Well, I have an advantage in that I can guess more often, correct? That doesn't necessarily guarantee that I'll win. It makes it more likely that I'll win, but doesn't guarantee it. Well, as technology kept getting faster and faster and faster and faster, the individuals who were mining Bitcoin had faster machines that could guess faster and faster. And all of a sudden what you had is you had some disproportionality going on between the people who were mining Bitcoins professionally and the people who were mining Bitcoins at the hobby level, to the point that if you were doing it at the hobby level, you would never win. You were just wasting electricity. So it would be the type thing where each of you could do one guess a second, and I can do 1,000,000 guesses a second, while it was theoretically possible that you could win. Chances are I'm going to win, right? Okay, and that really is what occurred. So what ended up happening is various organizations started creating what was called a mining pool. So that's a named pool that a bunch of individuals become part of and put all of their mining equipment together to try to win a block, to generate a block. So for us, if we wanted to become our own mining pool, rather than each of us working individually, we're all going to put our technology together and we're all going to guess simultaneously. All right, but each of us is going to be working on a different part of the guessing, so we're not guessing the same thing multiple times. All right, then that gives us, as a group, a better chance of winning than somebody else who has a group with less power. That makes sense? And then when the pool gets the reward of 25 Bitcoin, for in Bitcoin's case, then that pool has a couple of different technologies that it might use to distribute those Bitcoins. So the fairest version of that is, 25 Bitcoins comes in. During that last 10-minute block, I divvy up the 25 Bitcoins to each of you based on the amount of work you put in, based on the power, processing power you contributed to that 10-minute block. So pools come in that situation. Anymore, if you're going to be mining Bitcoins, I would say 99% of the time, you're mining in a pool. It's possible that an individual could spend so much money on equipment that they could potentially argue that they could mine on their own without being part of a pool and stand a chance, but it really is very unlikely. So pretty much everybody's going to be mining in a pool. So kind of some popular pools that are out there. Ghash.io is the biggest pool. BTC Guild is probably the second biggest pool. Slush Pool is another big one. Then you have, 5 or 6 other ones that people have heard of. And then everything else just goes into the little sliver of other. Okay? Now, let me ask you this. So based on what I just said, if ghash.io is the biggest pool, most power, most mining power, is that the one you should join? If you were going to start mining today, should you just be part of that pool? Why not be with the big guys?
Because you're going to get a very small fraction of anything that they gain, because you're probably not contributing that much power to the whole.
Okay, so relatively speaking, given the nature of the problem we're solving here, that just because you have the most horsepower, the most guesses per second, doesn't necessarily mean you'll win. Ghash.io, being the biggest, does win more often than the other pools do, but it still loses often enough. So when you are mining with ghash.io, you're a smaller piece of a bigger group. So when you do win, you get a smaller sliver of that 25 Bitcoin reward. Whereas if you were mining with BTC Guild, second biggest guy or third right now, somewhere in there, right? If you were mining with them, they win less often than ghash.io, but they still win sometimes. But when they win, now you're a little bit bigger of a contributor than you would have been on ghash.io's pool. So you'll get a bigger cut of that 25 Bitcoin. So the idea is that over time, as long as you're with a pool that has the capability of winning, you don't want to necessarily say, well, me and my 3 best friends who have spent $15 on Amazon on mining equipment, we're going to create our own pool. We're going to take over the world. So we're only dividing up our 25 Bitcoins amongst 3 people. We have never won. But one day the moons will align.
And it will all be worth it.
And it'll be all worth it. After all the electricity we've spent and stuff. So a pool probably needs to be of sufficient size in order to really stand a chance. But generally speaking, if you're mining on one of the larger pools, it probably doesn't necessarily matter from a money-making perspective, from a Bitcoin generating perspective over time. If you sampled those over 30 days each, you probably make about the same number of physical Bitcoins during that 30 days, regardless of which of the top 5 pools you're in. Make sense? So one thing that pools have to do is they have to determine how to optimally split the work. So at this point, we're theoretically talking about our guesses. A couple slides later, we're going to actually talk about what a guess is. Okay, but just generally speaking, let's just say we're guessing numbers. Okay, so the guy up who's running the contest says, I'm thinking of a number between 1 and 10 million. All right? And we've pulled our resources together, and we're going to start guessing at this number between 1 and 10 million. Now, we want to make sure that we don't guess 5 multiple times. That's a waste of a guess, correct? So how would you split up those guesses? How do we manage ourselves so that we're guessing in the most optimal way possible? Go ahead.
You take the amount of possible guesses, so
Okay.
10 million.
10 million guesses.
You divide it by the amount of people that are going to be guessing,
Okay.
and then you have each person is assigned a number, and you put them at equal spaces along the.
Okay, so you
line
assign
of
a chunk of it to
Yeah.
them. Okay. Now I assume are you considering everybody in this room to be people? We have a couple of questionables in the back there, Dane.
Sure.
Okay. Okay. So for the sake of this
As
example,
long as they.
for the sake of this example, they're people. Okay. So let's see. How many we got? Do I even want to count? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 people. So we're going to divide 10 million by 18 and get our chunk size, right? Okay. So that means each person in here is going to have their, they're just going to start guessing through theirs in order.
Yes.
Okay. So now let's say that our classroom criminal decides, you know what? I'm not winning this, so I'm leaving, but halfway through. So let's say it's a 10-minute guessing period, and he has his block that he's responsible for, and let's just happen to say that the answer is in his block, his collection. But he gives up. Okay, so he gives up and stops guessing because he's out. Apparently the timer went off. His blank money's done bleaching. Okay. What was I talking about? Oh, so anyways, how do we account for that? How do we expand our algorithm a little bit to support one of our miners backing out? Go ahead.
You give people that have more mining power bigger chunks, and people that have lower mining power lower chunks.
Well, then what you have is you've created a situation where people who have more mining power, they have a bigger impact if they decide to quit.
Oh, yeah.
So if you're the dude who can guess 1,000,000 times faster than everybody else, and you guess the first 2 and then just bail, your entire pool is done. So we need to solve for the problem of him backing out after 2 minutes with 80% of his guesses left, and nobody else knows about those guesses. Somebody needs to take them over. Go ahead.
Well, you look at the mining power for each person, and you still give them the blocks that they're in, and the people who are going to be faster are going to get done with their blocks first. And so what you want to do is maybe divide the amount that's left from his to the fastest as it goes down in the line of who's fastest, and you just divvy it up equally between the fastest people in your group. So you don't have to just stop what you're doing and then go to his block or something.
Okay. Isn't that kind of what he was saying, though? You're giving preference to the faster.
No. What he's saying is when they finish with, it's all equal sized blocks, and then when they finish with their block, they go on. They check to see if someone left, and then move on to doing
work
that.
on their stuff.
Yeah.
Okay.
Take over working on their stuff.
Okay. Now, what about this? What if, there's a central server that the keeper of the guesses, and you guys are all the ones who make the guesses, and the guessers, you people, you request from the server your next, group of guesses, and then you run through those real quick, then come and request again. So at any point in time, the list of guesses are all held in the server. That makes sense? And we keep track of what has been guessed and what hasn't. Now, when you drop off, if you don't come back in and check, how does the server know that, let's say you came and collected 10 guesses, and you completed 2 of them and then left. So there's 8 outstanding guesses. 8 guesses that you claimed from the server here, the server thinks has been assigned, but that will never get completed. How do we handle that? How does the server become aware that those 8 guesses haven't been accounted for?
Could you take the average time that the miner has spent on the chunks of guesses beforehand, and then if they don't come back within a little bit of that time, you assume that they left, and you hand that block off to someone.
So maybe we treat each assignment as kind of a work order, and a work order has an expiration time. And if the person who took it doesn't come back within a certain amount of time, that work order is abandoned, and now it's it's released again inside the server to be handed out to the next person who comes in for a request. Now, the best way to do away with this would be, well, I say the best way, the initial, most logical way of dealing with this would be only have a guesser request one guess. So you're going to come to me, you're going to say, what do I guess next? I give you the next thing to guess, you guess it, come back, what do I guess next? I give it to you, you guess it. What do I guess next? So on and so forth. What's wrong with that?
That's a lot of requests being made.
Okay, so, well, is that really a problem?
Depends on how many people are requesting guesses.
Let's say that I could keep up. Let's say I could keep up with those requests. Is it still a problem? The answer is yes. So my follow-up question is why?
Each time they have to come back to, each time they have to ask for another guess is taking time away from guessing.
From guessing. If you spend half your time asking for what you should guess, as opposed to actually guessing, you're only half as effective as you could be. So it makes sense to give you larger pools of guesses, correct? Now we got to play around with how large is too large, how large is too small, and then how do we recoup those? So there's actually more to mining pools than just dividing the work up, because you're very reliant on how often somebody sticks around. We can't have our all-star player start doing it, decide that, oh, I accidentally started on this pool, I actually belong someplace else, and then just bail on the pool. Same time, we also have to deal with the situation of time as it relates to rewarding for a pool. So let's say all of us in here are working on a problem. And the criminal was out bleaching. I'm not sure if I mean that in the same way I meant before. So anyways, he comes back in halfway through while we're working on the next block. Okay? So we're already off to we're half done. We're half done with our guesses. We haven't guessed yet though. We haven't guessed it right. Now you hit the server, ask for your request block, and you start working. And let's just say our pool wins. Doesn't matter which individual was the winner, but our pool wins. But he was only there half the time. Do we give him credit for his contribution as a whole to the pool, or only for the amount of time he was here? So now we have to subdivide it out, right? And with that, and we'll talk about it at some point, not in the next couple of classes, but at some point when we talk about some of the algorithms the different pools use, there's a couple of different approaches on how to assign rewards. So kind of a interesting thing. So there's really more to it than just, oh, let's divide up the work and hope for the best. There's actually some science in there, and also some time waste in there. How do we do it the most efficiently? Even within that, there is room for pools to continue to evolve to become more effective. If you have two pools that have the exact same mining power, let's just say we have two groups of people and both of our groups operate at the exact same speed. We can make the same number of guesses. It's possible for one pool to actually be more efficient than the other depending on how guesses are acquired. Make sense? So kind of an interesting client-server type model to discuss. Okay, so that's the stuff down here. All right, so now let's start talking about more specifically what these hashes are, what these guesses are. So, generally speaking, a hash is a one-way cipher. So what does that mean? An arbitrary amount of data is turned into a finite and fixed size hash value. All right, so I could take any one of your hard drives and run it through a hash and produce a single value that looks something like this. At the same time, I can take the email, the spam email you got this morning, send it through that same hashing algorithm and get a similar size value, similar value. So in one of those cases, I hashed a 1 terabyte collection of stuff. And the other one, I hashed a 1 kilobyte collection of stuff, yet still got the same output. So it's an arbitrary size input into a finite and fixed size hash value. That makes sense? Now, the other part of this, the one-way part of this, says you can't go back. Once you have this hash value, once I have this, let's just say that it's basically impossible for me to, if we take Amish's hard drive and we convert it into this hash value, it would be basically impossible for me to recreate his hard drive from that value. It's a one-way cipher. Make sense? Okay, so what's nice about hashes and why do we use them for this? Well, it's easy to create. If I'm taking that 1 terabyte drive or I'm taking that 1 kilobyte email, a hash is applied really, really quick. But just a little math problem. Spin through, generate a hash. Here's the unique value associated with the input data. Okay, so it's quick. And like I said, nearly impossible to recreate the block from the hash. Can't go back. So for us, our guesses are actually hashes. So how is a hash created in Bitcoin? And just to go ahead and give us an acronym, BTC is usually the representation for Bitcoin. Somewhere in here, I think I switch over to that just because I got tired of typing Bitcoin. They wanted to just put a space in between them, and I didn't like that. So I just switched. So how is the hash created? Well, we take the current block along with the hash from the previous block to generate a new hash, a new guess. So the hash from the previous block was the correct answer. So I'm going to take the current block. I'm actually going to take the header from the current block, which we talk about a couple more slides. So I'm going to take the current block, whatever that means. We'll talk about blocks. And I'm going to take the winning guess from the previous 10 minutes. I'm going to put those together with a couple other secret spices. And I'm going to generate a guess. And I'm going to throw it out there and say, did I win? And I'm going to do that over and over and over and over again. Okay? So this hash, along with the block itself, are stored at the end of the blockchain. So the blockchain is technically more than just transactions. It's also a collection of the previous winning hashes. Okay? And that's important for validation purposes. We'll kind of talk about that a little more soon, but we mentioned the 51% problem briefly last class, I think. And you get to the situation if somebody tries to rewrite the blockchain, technically, for everything from that point, the rewrite later should be broken because all correct guesses are done in terms of the previous correct guesses. Those hashes are taken into consideration. So if you hack this level up here, all of a sudden this is broken, this is broken, this is broken, this is broken, and so on and so forth. So somebody's going to notice. Just note that the blockchain no longer validates itself. Each hash becomes like a wax seal validating itself and every block after it, which is what I just said. Okay? If someone were to tamper with the previous block, everyone would end up knowing. So, like I said before, hashing is fast. A single computer can generate a hash in a fraction of a second. So just kind of pausing on that for a second, let's talk about how fast hashing really can be. In the early days of mining, people would use just their CPUs in their computer. And if you ran your, a modern day CPU, so let's go back to like 2009 when mining really started, and you used your CPU, you probably could mine at, let's say 3,000 hashes a second. 3,000 guesses per second. Seems pretty fast, right? Reasonably speaking. Now, how fast your machine can hash, how many times they can guess, is only as powerful as it is relative to all the other machines. So in the early days of Bitcoin, where not that many people were hashing, 3,000 hashes a second was probably, that's 3,000 or 3 kilohashes per second. That's probably would have been pretty decent. Today, it's a joke. Okay, it's equivalent to having a jar of peanut butter and saying that that is a hashing machine. Draw a little smiley face on it on a Post-it note. The chances of the jar of peanut butter winning are equivalent to your 3 kilohash mining machine. And I really think statistically that's an accurate statement. All right, so everything becomes relative of everybody else's speed. So as more and more people were mining, we started looking for better ways to hash faster, to guess faster. Okay, so what did we do? Well, we decided, well, we can use our CPU, but why not use our GPU as well, our graphics cards? Because graphics cards are special processors. So we talk about computer chips. How many of you have a Intel Core i5 or Core i7 processor in your computer? Okay, probably running at like 2.2 gigahertz, somewhere in that ballpark. Okay, whatever that means. And all of us have graphics cards. Anybody in here have a really fancy graphics card? Something pretty legit. Okay. So, which is faster, your CPU or your graphics card? Okay, that's a better answer. It depends. It depends. Okay. Now, how many? What kind of processors in your machine? You spend a lot of money on your graphics card, so I'm guessing you have a quad-core i7. Good guess. Okay. And yours is probably what, 2.6 gigahertz?
4.
2.4?
No, 4.
4 gigahertz? Is it AMD? I don't think they make a 4 gigahertz i7. They do? Oh, so you spent like tons of money on this thing. All right. I didn't know they made a 4 gigahertz i7. Okay, so is yours one of the 6 cores? Or is it 4 core? 4 core? Okay, well, in any case, so you got a super fast i7 processor, right? And it has 4 cores. So it can do 4 things simultaneously. Functionally, it can probably do 8 because it's got hyper-threading crap in it, but whatever. 8 things simultaneously. It's good enough for this example. Now, how many cores are in your graphics card? 1? 2? Is your graphics card a quad core? You're so quick with your answers to your processor. I'm guessing you researched the graphics card even more.
Yeah, for gaming.
For gaming. Well, how many cores does it have? So now I can't trust your 4 gigahertz number. My guess is, not knowing which graphics card you have, you probably have somewhere between 512 and 768 cores in your graphics card. So that means your graphics card can do as much as 768 things simultaneously. Which is faster, your graphics card or your processor? Still depends. Depends on what you're doing. The processor, CPU in your computer, is a general purpose tool. It knows how to solve a whole bunch of problems. Okay? I'm not sure it's fair to say that your CPU is Turing complete, but it's certainly way closer to Turing complete than your graphics card is and your GPU is. So your graphics card is really, 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 really good at doing math, specifically floating point math. That's really all it can do. It can do math problems really quick. Where your graphics card has a whole big list of magic tricks it knows how to do. And it runs programs, and the program says, do this magic trick followed by this magic trick followed by this magic trick, and poof, you have hello world on your screen. Okay? Well, if you're doing just math problems, though, your graphics card is very, very, very fast. In fact, over the last couple of years, our operating systems have started incorporating your graphics cards into their technology. Apple really started this with something called Opencl, which is actually an open source project that Apple kind of supports, and then put it into the Mac OS. And what it does is it takes certain types of problems and it offloads it off the CPU and puts it onto your graphics card. Certain problems, the graphics card is going to be more effective, specifically math problems. And it lets the CPU handle the things that the graphics card's too stupid to do. Make sense? It's not one of its magic tricks. Okay, so your graphics card is really a one-trick pony. Now, in any case, math problems. Hashing is a big, gigantic math problem. So our graphics cards are very, very, very fast at doing that kind of stuff. So what we started doing is we started leveraging our graphics cards for doing our guessing to generate hashes because they were faster at doing it. So that same computer that was doing 1 kilohash, or 3 kilohashes, 3 kilohashes per second, maybe now can do 300 kilohashes per second with a mediocre graphics card or a decent graphics card. When the graphics card in the big scheme of things, is far less capable than your CPU. But it just happens to be really good at the stuff that hashing needs. So we started using our GPUs for hashing. Now, if you were the guy who was sitting there hashing with your CPU going at 3 kilohashes per second and kind of keeping up with the Joneses down the street because you were one of 500 people that were mining, and all of them were mining on CPUs, and all of a sudden, 3 of those people starts GPU hashing, whoever came up with it first, right? All of a sudden now, you're disproportionately slow compared to the rest of the network. Those 3 guys are probably winning pretty often. They're their own mining pool built into one. Because what you started having is you started having people who would build mining rigs, which was just a computer with 4 graphics cards in it. And they have all linked together, and it was just mining, making guesses. So it was almost their own little mini pool until that wasn't fast anymore. Then we had something called Asics, application-specific integrated circuits. So rather than taking our general purpose GPU, which knows how to do a lot of different kind of math, let's take a circuit that knows only how to do this specific kind of math. Like, look, we don't need to do these kind of math problems, just this one. So we're going to build it into a hardware-based chip. And all that chip can do is hash. It can't even add 1 plus 2. Doesn't know how to do that. It can hash. Okay? So we start building these, then you put a whole bunch of those chips on a single thing, power it, and now you have all that happening very quickly. So those guys that were going at 300 kilohashes per second are now going at 300 gigahashes per second. We skipped right by megahashes. So the power of our mining equipment keeps going up, 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 which means that the $1,000 you spent last week on this latest, greatest, coolest computer with 4 graphics cards, blah, blah, blah in it, that was cool for the first 15 minutes, now can't even keep up. You're spending more in electricity by a lot than you are in reward from your Bitcoin mining. So when we say a single computer can generate a hash in a fraction of a second, we shouldn't be that impressed with it because we have pieces of mining equipment today that can generate millions upon millions of hashes every second. Now, Bitcoin has a requirement of each block being validated every 10 minutes. I say approximately 10 minutes, and we'll talk about that a little more, but that's a rule of Bitcoin. And we talked last time that every cryptocurrency that's based on SHA-256 at least, and we'll talk about what other options there are, has a block time. For Bitcoin, it's 10 minutes. I think we said it was 1 minute for Theory Coin. Different SHA-256 based coins modify that as to what they think is correct for their coin. But for Bitcoin, it's 10 minutes. So something needs to be done to make generating a hash more difficult. So let's go back to our early days of Bitcoin mining, where we're all sitting there with our CPU mining at 3 kilohashes a second, 3,000 guesses a second. And that's, let's say, the average speed on the network. We have 500 people on the network, so a relatively small community of miners mining at what is considered by human standards to be very fast, 3,000 guesses a second, but by modern day hashing standards, 0, non-functional, jar of peanut butter, right? Now, back then, having each block lasting 10 minutes, meaning it taking about 10 minutes before somebody guessed right, was far easier than today. Because now we're hashing substantially faster. So if we would have taken one of the problems from 2009 that maybe took 10 minutes for those 500 machines each doing 3,000 guesses a second, if that took 10 minutes, how long do you think that would take today? 5 seconds? And I'm probably exaggerating. I mean, it'd be almost instantaneous because the machines are so fast today, relatively speaking. But again, Bitcoin has a requirement of 10 minutes. It has to take 10 minutes. So we need to have something to fight against the speed. So as our equipment keeps getting, as the mining equipment gets faster and faster and faster and faster, we need to continue to make the job of guessing harder and harder to keep it around 10 minutes. And what sucks about that from a Bitcoin miner's perspective is, let's say that you go out and you buy a piece of mining equipment, one of these Asics, application-specific integrated circuits. ASIC is the name for it. That could pop up on a quiz sometime, FYI. Okay? Let's say that you go out and you get one of these guys. Here, you write it down. Asic. Application specific integrated circuit. This is a chip built specifically to hash. And most ASICs have a whole bunch of those chips wired together. Make sense? So this is what we're still using today, but even these guys keep getting faster and faster. And that's kind of what I was just getting ready to talk about is if we go out, if we 6 months ago went out and bought something, one of these ASICs for hashing Bitcoins, and let's say it hashed Bitcoins at 30 gigahashes per second. Okay? Well, that was a reasonable hobbyist speed 6 months ago. That 30 gigahashes per second in terms of what it would have provided you in terms of performance 6 months ago relative to the rest of the people in your pool compared to today has probably depreciated at least 80%. So it's 80% less effective today than it was 6 months ago. Because the equipment has gotten so much quicker and the difficulty of the network has gone up, which means that you play even a smaller role. You play an 80% smaller role today than you would have 6 months ago, which means that your profit, your cut of the 25 Bitcoin is 80% smaller today than it was 6 months ago. So it becomes a problem of keeping up with the Joneses. You know, what do you got to do? You buy equipment, you use it for 2 months, then you sell it before you kind of have three different levels of miners. You have the beginner, I'm just learning about it. You have the hobbyist, I'm interested in this, but I'm not going to drop $50,000 on equipment. And then you have the professional who is taking, you know, they're moving to new locations around the world where power consumption is considered to be, or you know, the cost per kilowatt hour of electricity is considered to be low, and actually building gigantic mining farms in those places. There's I think it's in North Dakota. There's a community in North Dakota. I think it's where the cheapest electricity in the United States is, and the real estate there is just booming because all these Bitcoin mining people are moving out to this area and buying these shacks and setting up just air-conditioned garages just filled with equipment. True story. So it's kind of crazy. And then what ends up happening is you have this sub-economy online where you have those professional miners who, let's say 2 months ago, bought whatever's the latest, greatest, fastest machine. And now there's a new latest, greatest, fastest machine. Those professional miners now throw that latest, greatest professional machine on eBay or something for close to what they originally paid for it, making it available to the hobbyists. So now the hobbyist feels like they're almost a professional. And that professional is making their money back so they can flip it and go and buy the next piece of equipment. It's a giant economy where the person beneath you just keeps getting screwed over. Okay, and why is that? Well, the hobbyist can't afford $50,000 for the latest, greatest equipment, but they can afford $3,000 for the previous latest, greatest equipment, which no longer keeps up because it's 80% less effective than it was when it came out. Make sense? But it really looks great on paper. All right. We're done at 3, right? We got 5 minutes? Okay. So anyways, Bitcoin has a requirement every 10 minutes, so something needs to be done to make that network more difficult, which then makes it less profitable for the people who've already spent money on equipment, so they have to go buy new equipment, which then drives the difficulty of the network up even more, so on and so forth. Otherwise, if we didn't increase the difficulty of the network, every Bitcoin that is ever going to exist would be mined in a matter of minutes. So we use that example of what used to take 10 minutes in 2009 would probably take less than a second today. Well, It's a lot faster. So we can't mine all the Bitcoins instantaneously. Because every Bitcoin that's ever going to be created has already been spoken for. The algorithm says that we're going to create, for the first 4 years, 50 Bitcoins every 10 minutes. Then after, I think it's 2016 blocks. No, that's every 2-week thing. But every 4 years, it halves. So now we're at the 25 Bitcoins per 10 minutes. Then it goes to 12.5, so on and so forth. So the very last Bitcoin, I think it's generated on some date, I think 2042 or something like that. Some date then. Maybe it's even later than that.
I think it's 21.
2140? Yeah, okay. So in any case, all those Bitcoins are already spoken for, but they're not based on a date. They're based on a number of blocks. Well, if we start mining blocks too quickly, well, we're going to generate all these Bitcoins too quickly. Well, that's where we need to keep to that 10-minute thing. So, introduce something called proof of work. And this is how Bitcoin does it, as well as all the SHA-256 algorithms. So the Bitcoin network won't just accept any hash. It demands that hash looks a certain way. So if we think about this, the guess has to look in a very specific way. That way is what we can adjust to make it harder to guess. Okay, along with a couple of other things. The network will only accept a hash with a certain number of zeros at the beginning of it. Now, an important aspect of hashing is when you make a guess, but if you look at the nature of the original data, there's really no way for you to guess at what the hash will look like. So you can't predict what your guess will be. You can't predict how many zeros are in the front. So the idea is that you're basically rolling dice over and over and over again until you finally land on the correct 2 to the 256 power times 2 to the 256 power, and you'll see why it's that number. A huge, huge number of possible guesses. So, like I said, there's no way of determining what a hash will look like before you produce it. Even a very small change in the initial value, when you hash it, will give you a completely different answer. It's not like the answer just changes by one character. It could be, they will likely look like they have nothing in common, the guess. So we introduced something called a nonce. And we'll start talking about this a little bit more next time, but just as a quick introduction, the nonce is something that we throw into the equation on top of our guess to try to add a little variability into our guess. So miners cannot change the data in the block. So we're making guesses. And remember that guess has to do with the current block as well as the previous correct answer, the guy who won the last block. That guess. All right, that's what the miners are using to generate that's 2 pieces of information they're using to generate their guess. Well, the miners cannot change the previous right answer. That's fixed, right? That dude already won, that was the correct answer. They also can't change the information in the current block. Those are transactions that are being validated. So the only thing they can change is this idea of a nonce. So the nonce is kind of what we were talking about earlier of that server that's giving you the pool of things to guess from. Okay, that's the part we're changing. And what we're doing is we're hashing this value plus this value plus this value. We're gluing them all together, generating a hash from that, and hoping for the best. Okay? So miners need to create a hash in the correct format. They do this by adding another small piece of information, this nonce, and that will entirely change the hash value. And this nonce is usually a 32-bit value in the SHA-256 algorithms. All right, so we're going to stop right there. Somebody remind me we stopped at nonces. Remember, we do not have class on Monday. It's Labor Day, so I will see everybody on Wednesday, and you'll likely have your first homework assignment that day as well. Have a good weekend.